Achso, bei mir heißt es wieder verbrennt. Nee, bei dir muss man mal stellen. Aber es lohnt sich jedes Mal.
So, Kalimera, good morning. Let's start the morning session. My name is Bernhard Mitschang, and it's my pleasure to chair this session and the session after the coffee break at 10:30. So we have 4 speakers in the 2 sessions. We start in the north of Germany, in Hamburg. We will have 2 presentations before the coffee break by Norbert and one of his research staff members, and then we have the break, and then we move further down in the German geo landscape to Darmstadt, and then we move to Basel, but we switch it around. So first there will be Heiko, and then there will be Uta. Yeah? Okay, so yeah, we are running around in Germany and then to Basel, so in the midst of Europe.
Nearly the same.
Almost the same. Everybody speaks German.
Don't talk too much, I have many things.
Okay, so not to spend his time, so let's start with Norbert Ritter, and he will tell us a little bit about data management.
Thank you very much.
Scalable data management in the cloud. Is there any more to say?
No.
Okay.
So thanks for the introduction, and thanks to Frank and the board for having us again. It's a pleasure to be again part of this nice conference. And that you gave us some space in the program for doing that session, because it's not only a topic of my presentation, it's a topic of the overall session this morning. And the background is as follows.
Oh, this was my part.
As you see, I'm going to be talking about scalable cloud data management, and this on one hand is kind of the topic the most of the research we did and we do in my group in Hamburg relates to. And we want to remind you of a few things we have already presented on earlier SummerSOCs. And I wanted to relate them to that topic, and I want to tell you what we want to do next, and what we think what needs to be done in order to make scalable cloud data management a success. The second thing to mention here is that Felix Gessert, who was also here, and myself, we are organizing a workshop with exactly that topic about scalable data, cloud data management, and it's held together with the International Conference on Big Data, which is this year in December in Los Angeles again, and we will have the 8th workshop in a row. So we'll give you the coordinates at the end of the talk, so possibly if you want to submit a paper, I would be happy to see some of you there. Okay, then I want to directly jump in. I have millions of slides, and I try to manage to get...
Don't show all of them.
So what's cloud data management? It's an abstract definition or introduction saying you should tackle the design, implementation, evaluation, application, implications of database systems in cloud environments. I'm going to be more precise later on. And if you want to do that, you have to take care of, you tackle a lot of problems, and you have to solve things like that. What's the best application architecture? What are the best data models for the applications? Which protocols, APIs, and which caching mechanisms are to be used at the interface between the applications and let's say the middleware which is representing the cloud environment. And there you have to deal with things we have already been talking about in this conference, like load distribution, auto-scaling, service level agreements, workload management, metering, and so forth. And the back end, you have the data management. There you have to think about things like how to do multi-tenancy, what about consistency, which is a very interesting topic with respect to NoSQL database technology, which you will find here primarily. What about availability, query processing, security, privacy? You know that consistency and availability is a very, very interesting duo, because in terms of NoSQL systems, you always have to trade-off between consistency and availability. And many things we have to do currently to manage trade-offs. Yeah. and to decide whether availability is more important for us or full consistency, and to tune the systems like this. And additionally, you have, oh, there's privacy just for.
Ooh, you put it in last night, I know.
Yeah.
And you move it up from the top.
Yeah.
And then you have to deal with things like replication, partitioning, transaction, and so forth. You have to rethink many things which were there in traditional databases, but now need to be thought new because you have a totally new environment and new conditions for doing all that. So if you look into current approaches, we always try to bring some order in that multitude of approaches and systems which are currently out there, and trying to arrange them in such figures. And you can distinguish different degrees on how managed these systems are. You have cloud deployed databases. You have managed cloud hosted databases, and you have proprietary data cloud systems. And I will show you in a minute what that means. And here we have the degree of structure in the data, and so you have the relational thing, the schema-free, NoSQL thing, and the analytics out there. And this is what we focus on, because we want our cloud to be managed, and we think about how to do this management appropriately in order to fulfill the needs of the application space. Yeah. So let's go a little bit into the different things. What you have in the case of cloud deployed databases, they use an infrastructure or platform as a service cloud to provision an operating system and a database system as a Park application. So that means you have your own installation, it's just remote, it's in the cloud. And you have to do everything you would have to do if it was on your own device. So what you not have, and what this approach does not solve, is all the interesting things. How to provision, to do backups automatically, security, scaling, elasticity, performance, tuning, failover, replication, and all that. Yeah, because it's your own responsibility to do that. So this is not what we want. Then we come to a second approach, which we call managed databases or cloud-hosted databases. Here, the service provider is responsible for things like configuration, scaling, provisioning, monitoring, backup, privacy, and access control, and so forth. And this is what managed means. Yeah. And there are many examples out there. For example, cloud-hosted relational database systems. These are just some examples there. Cloud-hosted NoSQL databases and even data warehouses. Yeah. So when you kind of are allowed to work with these systems by using the interfaces they offer, but the management in the terms of things I mentioned earlier is done by the provider. Yeah, and this is what gives you some additional value for having your data in the cloud. There are also proprietary solutions. They are the same way managed than in the approach before, because it's the full responsibility of the service provider to do the management. But things are proprietary in terms of the service provider has the ability to do a kind of co-design of the cloud infrastructure itself and the data management component. And it's not a given database system which is deployed within the cloud and managed by the provider. It's a kind of co-designed thing, and you have proprietary interfaces there. But it's fully managed, and the provider has to do all the interesting things like elasticity and so forth. And here again we have some examples for databases, for proprietary cloud databases and object stores. And here you usually just can store blocks or something in the cloud and get them back. Okay, so there's something similar for analytics as a service. It looks like a proprietary thing. The messages hold also for managed analytics as a service things. The examples are these for analytics, and Google does provide some support for machine learning. terms of classification and clustering mechanisms, which can be used like this. So, but still, this is not what we aim at. What we want to do is this. We want to design and develop components for what we call backend as a service. And here, you have not only a data API, but also you have some kind of, how to say that, common business logic elements. So those business logic functions which can be used by many applications. For example, user management. Yeah, I can directly. These are the examples, and this is our approach, and we kind of did a lot of research in that area, and the results of this research are now kind of the subject of a startup which is called Backend, and which Felix, which I mentioned earlier, is the founder of, and which today has about 20 permanent employees, and which are kind of selling this as a product what we developed in our research. And I think this is a better slide to explain all this. So as I told you, many access and application patterns are very similar across different applications and can therefore be standardized. And this is what you have here in the business, in the function as a service component. And additionally, you have this database as a service thing. This is very similar to the managed approach we had earlier. And you have standard APIs, and it's the responsibility of the backend as a service provider to do all these interesting things. We will talk about later on how we can do that. And then you have all the backend as a service APIs, and from them you can also already see what are some of these components which are useful for many applications.
Is the mental model that you use fast like stored procedures do in traditional databases?
Sorry?
Is my mental model correct that you use function as a service fast?
Yeah.
Like traditional database use stored procedures, bring the logic close to the data?
Right.
Ah, okay.
But it needs to be some logic which is used for many applications, because we are a service provider, right?
Now, can I write my own fast and inject it there and you manage it for me?
Usually this is what they provide for everybody, but you also have the possibility to extend that. So and then usually what we have here are clients which are possibly mobile web applications or you name it, whatever, which are all accessing the cloud via wide area network. So then you directly have the latency challenge, and you need to care about how to deal with latency. And they access the cloud by using a REST API, which is based on HTTP.
The functions as a service are not directly interfaced at the REST level, or are they somehow hidden in the query, search, or other stuff? Or those functions?
Those functions are directly provided to the users. They are accessible.
So it's backend code.
Yeah, they are accessible through these APIs, which are available for all the applications which use the cloud, right?
But I can also have a function FAAS that I directly interface.
Yes. Yeah. And the thing not mentioned so far is you can also use this component to connect other services to these environments. Yeah. So, and since I said that this is what we aim at, we can look a little bit into the properties or in the things we think are important. So it's a rather trend, and as always, this progress is currently driven by industry projects. There's no structured research on it. And this is what we had several times with database management, that we made a theory after the industry was successful in doing things practically. And I think we should kind of take over and provide solutions for the major problems in corporate research. We like it best because it's most comfortable for the applications, but there are many problems which need to be tackled. So the latency challenge is what we tackled so far. We'll give you some ideas in a minute. how we do that. We have this challenge because our clients access the service by a high latency wide area network. And you have persistence on top of one single database technology currently. Okay? They have as this component usually one NoSQL database or something. And then you have to live with the capabilities of this system. And as you know, there is a multitude of NoSQL systems out there currently. They all somehow manage the availability consistency trade-off in some way. So this is what we kind of cover by a very broad notion, which is called eventual consistency, but there are many very special things behind that. And the point is that each of these systems, really there are hundreds out there, do have their own specific properties and advantages and disadvantages. And it's very hard for an application to kind of find that NoSQL system which best fulfills the requirement of that application. Yeah. So, and that means if you have a one there, you have this problem, does that really fit for my application? So what we want to do is we want to make it polyglot, so that we have different technologies as a database component within the cloud, and then you again have the problem how to mediate, or to orchestrate that, how to coordinate data processing on a multitude possibly of different database technologies. And if you only have one, the second problem is they map all tenants to the same database system, and you can configure the database system only in one single way, and then this configuration holds for all the tenants. For example, the replication protocol. Okay? But possibly it would be more appropriate to configure it differently for me than for the others, so forth. Yeah? And that means this is a good approach, but it's not flexible enough. Yeah? And this is somehow what we want to tackle in the future. Service level agreements, we had that in Stefan's talk on so I do not need to tell you what it is and what the objectives are and how to make them measurable. And this is a traditional approach we had in data warehouses, for example, to kind of arrange these things. This is these are the published resources on which we do scale in and scale out, and we all remember that from Stefan's talk there. The thing, the message I want to make here is this one. So if you look into some of the system, and it holds for many others too, we don't have anything. So there are some which have simple uptime as the only service level objective. Yeah. So and that means on one hand you have to kind of find the right system for your requirements, to select the right NoSQL systems for your requirements if you build a new application, and you cannot specify your requirements because they are not able to deal with service level there.
But the reason is they probably don't have the internal functions.
They don't have the mechanism.
Yeah, they don't have the mechanism. It's not only a question of providing them to the outside, but they cannot.
Right. So this is what I mentioned, that we should talk together and bring our things together, because that's what people would have there. I think. So this is again a table I don't want to go into. I don't remember even all the elements in there, but I just want to say that this is generally how we do things. We look into all the systems, we try to compare them, we try to categorize them, and then draw our conclusions. And the thing is again that also these managed NoSQL services are completely different, and it's really hard to find the right one for your purposes. And then this is for me the reason to make these things more flexible and to cover a broader range of requirements in order to serve a broader range of applications. So, and this is okay. What did we do so far? Yes.
We had a look in the SCRS NoSQL architectural tactics. They have this kind of expert system.
Felix certainly did. I don't know any details about that. So
I wouldn't say it's a perfect solution, but at least it helps a lot.
and this one first.
Yeah, I mean, this is basically like expert system guiding you based on
Ah,
the requirements to the NoSQL
Okay.
database you should use.
Yeah. Okay. Yeah. I remember that. But that's a good research prototype.
Yeah.
We need to take into account when we go further on that. So what's our CDM, Scalable Cloud Data Management approach? And now I will kind of remind you a few things we presented already in earlier SummerSOCs. A few statements. We want to aim at a fully managed backend, so we kind of follow the backend as a service idea. The first thing is we want to exploit modern NoSQL database technology, and in a sense, I was telling you earlier that you need to understand all these system capabilities, and you need to find a way to map requirements of applications to the capabilities of systems. We did this NoSQL database survey and decision guide, and this is the first thing we did present at SummerSOC so far. And what we did is we came up with a very simplified decision guide. And this goes back onto the capabilities and the techniques which are used by the corresponding systems and how they relate to functional and non-functional requirements. And this, in the end, allowed us to kind of provide such a decision tree. For example, if you have complex queries and the volume is unbounded in the sense that it does not fit onto a magnetic disk or something, and you have a top queries, then we recommend you MongoDB. It sounds very easy, but much more complicated because this is what is behind. We looked at the techniques the systems use. We did a very in-depth analysis and looked into the techniques they use for sharding, replication, storage span, and query processing. And then we kind of related functional requirements applications might have and non-functional requirements, all those things we are all the time talking about, to these techniques and how they kind of help to fulfill these requirements. And then we built a toolbox, and this is the background of the tree here. And if you need a more fine-grained information, then we did tables for most or many more those shown here, and kind of related to the techniques and this way the requirements which can be fulfilled to these systems. So this should help people to find the right system. And we want to use now these systems, and we want to kind of use an appropriate number of these systems, covering the most relevant application requirements, put them together into a backend as a service cloud, and find some way to mediate between the systems. And this is what we mean by fully store, and for example, Felix and Heiko as well will be talking about that. So what we have is NoSQL database system support applications in achieving horizontal scalability and backend performance through differentiated trade-offs in functionality and consistency. And then the next thing what we did is we checked out the scalability challenge. So if you remember that all clients in the backend as a service cloud do access the cloud via internet, via HTTP, and then you have a situation like this.
That was unchecked.
Last time in my lecture, my watch said, das habe ich nicht verstanden. Okay, you have a mobile client over there, you have a backend there, and then somebody clicks on a link on its mobile, and then data needs to be done. The website needs to be kind of rendered, and the data needs to be processed in order to deliver the data, and then the data is transferred via the network to the mobile application. This is what you know, and this is usually means high latency.
You want to say you are transferring all your data to the NSA?
Yes, exactly. This is why I'm choosing exactly this example. So, how can we reduce latency? Increasing bandwidth is not a solution, because this is the observation. 2 times bandwidth leads to the same load time, but if we have half latency, we really have half load time. So we need to deal with latency. What do we do? we exploit web caching. And this is our backend as a service approach as it is designed. So far it's called VSiS, and VSiS is the thing I mentioned, the result or research I mentioned, which is now the subject of the startup backend. They sell this as a service and further develop. There we assume to have a polyglot storage, but currently that means we have Redis, MongoDB, and Elasticsearch. It's not a really polyglot persistence mediator. This is what we need to do in the future. But we have some of these systems. We have, this is the, let's say, the component, the application server, which, for example, also provides some of these function as a service modules we have been talking about earlier. And it provides caching, transaction schemas, invalidation, detection, and so forth. And additionally, some real-time querying. So, and then we exploit standard HTTP caching. So if you really want to reduce latency, you have to do something which is compatible with HTTP, because we don't want to change the internet. We want to make our solution which reduces latency compatible with what is there. And then we have the Unified REST API, which applications may use to talk to the VSiS application.
You mentioned before that to deal with security, access control, isn't that the concern?
That's all a concern, and then
okay.
yeah. It's
okay,
some
transactions.
We have solutions for that. I can't go into that. We have a brilliant PhD work which is totally finished, which all these things, but I cannot go into. So, and what we do is the following: we exploit web caches. That sounds easy, but every time it is possible, we just use the data which is in the cache. So you know, in the web you have many caches. You have server caches, reverse proxy caches. You have you name it, until you have the browser cache and so forth. And each time the data is transported through the web, it passes many different caches, and copies are stored there. The problem with database data is that you have concurrency, and that data usually gets stale. It outdates in the cache. So you need to find a way to efficiently indicate the application that the data which is in the cache and which is close by is still current and can be used. And if not, if it has been changed in the backend, then it is necessary to go through all the way through the internet to the backend. And what's the core of this PhD work is a simple Bloom filter approach, which we call a cache sketch, which kind of maps all the objects to the Bloom filter and indicates which of these objects are currently updated. And we found an easy way to provide applications which, with the current information about the staleness or non-staleness of objects, and the Bloom filter is a very compact approach. So here's the overall solution. You have an access of a web client to database data, and then, for example, we have CDN caches, the browser caches. Only there are many more in the chain, but these are only two examples. And then you have copies in these caches. These are invalidation based. These are expiration based. It's another challenge because you have to specify a time to live, and afterward the data is considered to be stale by the cache. So, and what we do is, if data is delivered and then a concurrent client does an update in the backend, then we specify this modification in the Bloom filter. The invalidation caches are informed, and there are ways to efficiently kind of deliver this small Bloom filter information to the web client, so he does see whether or not the data which is close to him is still current or is stale.
Do you have your own CDN?
No, but this is the only thing we need to do. We work together with CDN providers, for example. For example, with Akamai, when they integrate our mechanisms. Yeah. Yes, and it works like this. You have an idea how it works. It's much more complicated, and it's the subject of the PhD thesis of Felix, which finished his work separate, so it's pretty. So, for example, if you have 20,000 distincts update with a 5% error rate, the Bloom filter is only 11K. Yeah, so it's a very compact thing, and you can exchange and change it. So that does not mean that the application necessarily does always have consistent information, but it can choose. Yeah, there is some, what's a sheep regulator, a sliding control, a sliding bone speed. They can choose how stale or how current they want the information to be. Yeah. And this is the intervals in which the Bloom filter is delivered to the and this is, I think, a very interesting thing. Okay, the next thing is make the thing push-based. Yeah, in the database management, we are pull-based. We ask queries and get information back. But what we also need is real-time queries or continuous queries. We want to subscribe a query, or register a query, and each time an update comes in, we want to be notified whether or not the result set of our earlier query would change as a result of that. This is the core idea of a second PhD thesis, which is also finished now, and Wolf from Lingerath had its defense in May, so it's pretty interesting. So this is the general research question: how can we expressive push-based real-time queries to be implemented on top of such a NoSQL database or an arbitrary database? It must be flexible and must fit to several of these technologies. And what we did again, we looked into the systems which are there. I talked about that the year before last year, I think. And we looked into all these real-time systems and how they do continuous queries, how they support them. It's usually pull and diff or changelog clearly. And the basic thing is they do not really scale. Either they do not scale in the number of writes, or they do not scale the number of queries, yeah, to the mechanisms they use. So this is not true for us. We scale, and then we try to find out how to realize such a real-time component. And for that, we considered stream processes. Kostas was talking about SumSOC on Monday too. And the thing is here that Storm and Flink show sub-second latency. They are the fastest. Right? Flink is much better, easier to use, has a better interface, has more function than Storm. And Storm is a very rudimentary, hard to use system, but it's the fastest. So for all purposes, that was enough. Today, I think we would choose Flink, but 2 years or 3 years ago, we have chosen Storm. And what we did is the following. The user may register a query. The query first is evaluated. The result is transported to the InvaliDB cluster, which is responsible for the real-time query. It's delivered to the application who asked the query. Then the query is active. As soon as an update comes in, this update is sent to both the database and to the InvaliDB cluster, which then, in a scalable way, finds out whether or not this write changes the result of the earlier registered query. Yeah? So, and how to make this scalable if you have a highly frequent stream of write ingestions. Yeah. So, and these are the general problems around, don't want to go into, and this is how we did that. We used Storm, and you can have many queries, you can have many writes, and you need to find a way to do the matching in an efficient way. What we did is we provide a cluster of nodes, a Storm cluster, which consists of the columns of query partitions and in the rows. So So each time a new query comes in, we associate the query with each node in one of these rows. And then when writes come in, we give the writes into the rows, and so each query gets once the write, the update information in order to check whether or not something needs to be negotiated. And because of this cluster, which so we get the write into the row so that every query is taken into account, and then we possibly find out that there is a change in the result set of a registered query, and that the corresponding client needs to be informed. Exactly. And we can easily do scale out in terms of kind of extending the overall cluster, storm cluster. So this is the idea, and we have evaluated this very, very intensively and find out that this is very efficient. And it's getting in scales, the scales in the number of reads, and the number of writes, and the number of
improved it by
yes, we improved it by evaluations.
So you only use Storm here?
We use only Storm.
Why don't you mention Kafka? Or
No.
Is that in the same class?
No. And Kafka is not a stream processor. It's the mechanism within SumSOC, for example, as Costa told, which is used to make the Kafka
So
nodes communicate. It's actually a message passing construct. So that is what we did. And as I told you, backend does a lot more than just providing the caching thing. What they do, for example, is they have a speed kit, but this is just an additional information which allows existing applications, which have the existing backend, to get pretty much faster by kind of incorporating the caching mechanism into their system. Yeah? So we bypass no, that's not the right word. We kind of put the speed kit in between the application and the original backend, so that the load of web pages is done via our caching infrastructure. And this can be easily incorporated into existing systems. And this is what we, for example, did here. This is an example for Bauer, and you get some idea how much faster things are. So in these web applications, e-commerce applications, milliseconds to really count and matter. So yeah, this is just an example. But this is just an additional information. They find it very good, and the vision actually is, oh my god.
Yeah.
What now is open is the polyglot persistence mediator, and this is the background. Usually you have applications which have different kinds of data, for which different kinds of database, especially NoSQL technologies, are well suited to serve the corresponding requirements. So for example, if you have an e-commerce application, you might have financial data, and for that purpose, relational databases still are the best solution. You may have session data, product catalog data, clickstream data, full text data, social graphs, and so forth. And for all these different kinds of data, you actually should use different kinds of database technology because they differ in their capabilities. And for that, we currently think about how to kind of possibly do some kind of automated mediation, or up to which, Crete doesn't make sense to work with an automated mediation of several systems. And this is the idea, to have certain application layer which kind of mediates. And mediation means not only orchestrating several of these NoSQL systems, we need to map the data on the background of the requirements of the application to the right database. And what we do here is, this is the vision, we want to kind of make the users annotate their schemas. So we have an annotated schema, because several parts of the schema, certain parts of the schema may have the requirement of low latency.
If you have a schema.
Yeah, if we have a schema. Yeah, so we usually have schemas, and we need to kind of deal with that. We need a schema which can be annotated, and then the system can kind of route those parts of that schema to the appropriate NoSQL database, and then you later on also need to do the well-known query rewrite mapping thing. Yeah, we know from information integration. So we already have some ideas. These, for example, are the annotations which we think make things. You have continuous non-functional, binary functional, and binary non-functional things. Example, read your writes, which is a certain degree of consistency you can get by choosing a certain NoSQL system. And then you can annotate the schema like this, and then we have an idea of some algorithm, which kind of rank algorithm, which does not recursive descent using the annotated schemas and metrics, and then gets to kind of topology of systems, which is useful for that special application. And then we need some component which during runtime is able to orchestrate the system in order to answer the queries of the application. So, and this is what we call the polyglot persistence mediator, and how to really, so we have first evaluations on that. So we directly implemented that for this example, where you have news articles, we need to manage news articles with impression counts. So you directly see there is one thing which is the management of text of articles, and on the other hand you have a counter. Yeah? And if you put that in the same database, for example MongoDB, which serves the management of text data very well, but the counter would kill the performance. Because every time you update the counter, you have concurrency and blocking and things, and this is not what you want. If you do it in Redis, then it's the other way around. It serves the counter well, but it does not kind of support the management of documents. Yeah, and this is so we did that. We split it up, and we did some measurements. And this is, for example, is Orestes without polyglot persistence, and this is Orestes with polyglot persistence. It's obviously better, but we need to do more work on that. So, and these are the primitives, especially live migration. So what are the primitives on how all these systems you have in the backend may properly work together? And how do we coordinate it? And do we learn during processing, monitor information, and learn how to possibly change the topology of the systems and possibly do some live migration of data during runtime? Does that make sense? These questions are those we want to tackle in our future research, and this is what Felix wants to talk about now. So, many more things. This is what I was talking about. No, I don't talk about transactions and stuff. We have many applications there. For example, this backend block is pretty interesting because everything we did is there, not only in the scientific publication. These are the two guys who did most of the work I was talking about in their PhD thesis. There's a book on real-time, there's another book in the same series, which is to come soon on the caching. And this is the workshop I was mentioning, which is in December in Los Angeles, together with the IEEE Big Data Conference. Please submit a paper, and then we can
Submit the paper and join.
Yes.
Thank you. Felix, maybe you just move up there and show your stuff. While he's doing that, we can have some questions or comments. Thomas.
You mentioned that the demand for this backend as a service thing is driven by industry.